Good afternoon, everyone. Today we have our third lecture on quantum computing. As usual, there will be a quick revision of what we did in the previous week, and I hope you had plenty of time for revision. And concretely, last week we introduced complex linear algebra and then started describing systems using linear algebra. And what we did is we started with deterministic systems in which we said we can represent our system as a graph, and we have transitions between the nodes or vertices. And with a deterministic system, we had a certain number of marbles we could move around. And we introduced that we can represent our graph as an adjacency matrix, which denotes the transitions from one vertex to the others. And we saw that if we take this matrix and multiply our state vector, which is a column vector representing the state of our deterministic system, we multiply this from the right. What we do is we do one transition, and then we have the new state after that one transition. And we saw if we multiply this matrix with itself, we can represent two transitions at once, so two time clicks with one matrix, and so forth. The deterministic systems were only necessary to establish this mechanism and make sure you don't mix up rows and columns in this matrix. So do exactly the notation we have established before. And then we started making these systems increasingly more complex. And concretely, what we built was probabilistic systems in which we have one marble, but we don't know exactly where it is. Rather, we think in terms of probabilities, and then our state vector for these individual positions needs to add up to 1. And we use exactly the same kind of mechanism that we used before, that we use a matrix to describe, or a graph to describe the transitions. We can multiply our state with the matrix, and we move in time by one time click into the future. There are some rules about these matrices. Concretely, they need to be doubly stochastic. That means each row and each column needs to add up to exactly 1. And we also saw if we transpose the matrix, actually, we're just undoing the operation. So we go back in time by one time click. We can do the same if we take the matrix, the original matrix, and multiply the row vector from the left. We're also undoing that operation. We're going back once in time. And we introduced this time symmetry to describe this. All the things we introduced, like you can multiply the matrix with itself to do multiple time clicks, it's here the same thing as before for the deterministic systems. And we introduced this stochastic billiard game. And today we'll continue actually with the billiard game from a quantum perspective. And the stochastic billiard game looks this way, that we have a doubly stochastic matrix. We have 4 states, or we have 4 positions, 0, 1, 2, and 3. And our start state starts in vertex 0 or position 0. And after one time click, we are with a 50% chance each in vertex 1 and vertex 2. We do one more time click, we're with the same probabilities, 50% in 0 and 3. And then it just keeps alternating. That's what we discussed. We also briefly looked at the probabilistic double slit experiment, and we introduced this in detail and built this matrix. But this matrix is not doubly stochastic, so it's just trying to mimic the behavior that we want to see later, or we're going to see this from a quantum perspective, and it will behave different. What we saw is that if we do the experiment, so we start with the start state and we do 2 time clicks, then we're in these targets. But since there are 2 ways to get into 5 from 1 and 2, there's actually the double chance that we are in this position when we run the experiment from a probabilistic perspective. because this was this 1/3 probability which we introduced. Now, we will see a quantum experiment of that sort today as well. And then we started modeling quantum systems. Why do we care about quantum systems? Well, this course is about quantum computing, so we want to make it to quantum computing in the next few weeks. And what we need for that is quantum mechanics, and our systems we had built so far are probabilistic systems, but we learned before that quantum mechanics can also be seen as a generalization of probability theory, and thus we built now quantum systems. And these quantum systems, they come with some interesting properties because we use complex numbers, both in the states as well as in the transitions. And then we can see that probabilities, complex probabilities, can actually cancel each other out, an effect we call interference. And that's also something we're going to study in greater detail today. And there is a constraint for valid quantum states. We've seen before for valid probabilistic states, all the entries need to add up to 1. For our quantum states, all the modulus squared of the entries need to add up to 1, because all of these are complex numbers, even though maybe this one only has a real part and this one an imaginary part. They're still complex numbers, and the modulus squared of the entries need to add up to 1. And then we have a valid quantum state. And we've seen this state last week, and we saw it's a valid one. And all of our transitions can also be described in terms of complex numbers. And that's something we did, and we wondered, why do we need to do this? And then we came back to the concept of unitary matrices that we also introduced in the beginning of the last week's session on complex linear algebra. And with, just remember, a unitary matrix means we have a matrix U, and its adjoint times itself is the identity matrix, or the matrix U times U dagger is also the identity matrix. And that allows us to undo the operations in U by multiplying in the U dagger. And remember, the adjoint, which we call U dagger, is we take the matrix U, we transpose it, and we calculate the conjugate of each entry, means we change the sign of the imaginary part. And if a matrix U times its adjoint, or the adjoint times its matrix, if we multiply them, these two multiplications in both cases need to lead to the identity matrix, which just is a neutral element in here. We finished here last week, and I want to know from you, first of all, if you're okay with what we did last week. Last week, there weren't that many students in the live stream because we were doing a stream one day earlier. So I hope you had enough time for revision. Maybe just send me a thumbs up if you're okay with what we did last week, or a thumbs down if there are any doubts or issues. So it looks you're all okay. So we can go ahead with our course, and I will very quickly switch back to the iPad. Just give me a quick moment to get this started. Just takes a second. Somehow got stuck. Need to see what the issue is. So finally, the screen share is working. Then last week we did the billiard game, and we now want to do the quantum billiard game. And for the quantum billiard game, we're going to use quantum mechanical effects to get it working. And so we'll do the quantum billiard game. And I will first draw the graph of what the quantum billiard game will look like. And this time we will use complex numbers. And then we will see how it actually behaves compared to the probabilistic one from last week. Do you remember the probabilistic experiment? We had a half probabilities, which were real numbers. This time we use complex numbers, which only have a real component. And some of them are positive, some of them are negative, and it's each time it's 1 divided by the square root of 2, but it's complex numbers, and some of them will be negative. All of these examples you can also find in the course book. Hope you had some of you had a chance to look into the course book in the meantime, and it will turn out to be very helpful for further readings and revisions if you wish. Then this one here is the negative one. And you all saw last week how we can turn such a graph into a matrix. And I want to know from you, let's say, what the first row of the matrix would look like that represents this graph. It's also a quick revision and practice for you. So just send us in the chat what the first row of this matrix that represents this graph, so the adjacency matrix, could look like. And oops, I just forgot it's to add the numbers here. So that's correct. And once you have an answer, you can send this to the chat. So we got the first suggestion, which is correct. Remember, for the first row, we want to see the incoming arcs for position 0. Since there's no loop for 0, this is a 0. It has nothing incoming from 3, so there's a 0, but from 1 and 2, it has incoming ones, which are 1 divided by the square root of 2 each. So, hope this was a good practice for you, and I'll just provide you with the next rows. So the incoming ones for position 1, from 0, it's 1 divided by the square root of 2, no loop. It has nothing incoming from 2, but from 3, it's 1 or minus 1 divided by the square root of 2, which is this one here. This one coming in. And I'll just continue now with the last 2 rows because you should know how you can derive this. But so it's 1 divided by square root of 2, 0 and 0, and 1 divided by the square root of 2. And for the last row, it's for element 3. There's nothing incoming from 0 and no loop, so 0, 0. But then from 1, it has this negative 1, 1 divided by the square root of 2, and from 2 has 1 divided by the square root of 2. What I want you to do now is imagine you start with a start state that we call this 1, 0. We just write this matrix is A for now. And we have our start state, which we can call X. And we have matrix A. And I want you to multiply your start state X from the right with matrix A, and we will get a state that we will call Y. And with that start state, we denote that we start in the element 0 here, and we do one time click of transitions. And once you have the state, please send it to the chat. So it's your task now to multiply this vector with this matrix from the right, and we'll compare what it means. This one, since there are lots of zeros in, it should be fairly easy for you to multiply this vector with our matrix. But I'll still give you a few seconds to submit your vector here through the chat, and I'll see if anyone we got the first answer. So since we only have a 1 here and we have lots of zeros in the matrix as well, the first one here is 0 because we have this 1 multiplied with this 0, and all others are 0 anyway. What's interesting is the next element. It's 1 divided by the square root of 2. The next one is as well 1 divided by the square root of 2. And the last one is 0. We will see later how we can actually interpret a complex probability that is 1 divided by the square root of 2 and not just a half. But in fact, what we have here as well is a 50-50 chance that our particle is in position 1 or 2. Even though this probability here is a complex one, it's 1 divided by the square root of 2, not 1 divided by 2. We'll see later how we can interpret this correctly. But these are the two entries. They have exactly the same value, and we knew they need to add up, or at least their modulus squared needs to add up to 1. So we can say here we have a 50-50 chance that our particle is in positions 1 or 2. Now, what I want you to do is in the next step, we multiply our vector y. So this here is y that we've just derived. And I want you to multiply this vector again with a. And once you have an answer for this, please send it here to the chat, and we'll compare what you got out of it. And we'll see if this actually differs to the result we got from the probabilistic one. And we already got the right answer here in the chat. In fact, what we get is a 1, 0, 0, 0. It's fairly easy to multiply this vector, but the only elements that really matter are, or the rows that matter are these ones, because we have otherwise just these zeros canceling each other out. But what happens eventually when you multiply y, our second state vector, with a, we get 1, 0, 0, 0, and one of you already got this and sent this in the chat. So how does this compare to our probabilistic billiard game? You can either send this in the chat or raise your hand, turn on your microphone. I'm happy about any contributions you're making, and let us know how this actually differs, or if it differs, to the probabilistic billiard game. And maybe rather than sending a long text here in the chat, if you remember the comparison or you see any difference, maybe just raise your hand here in Zoom, and then turn on your mic. So no answers, that's fine. It's actually totally different to the probabilistic. Now we got this here in the chat. And one student says we come back to a certain state which is equal to the start state, where with this was not the case with the probabilistic experiment. That's true. So with the probabilistic one, and I said this before in the revision, we just bounced back between 1, 2 and 0, 3 all the time. But here, actually, after the second time step, we go back to the start state. So why is that the case? Well, it has to do with these negative probabilities, because, for example, we have one here. And because we use complex numbers, we don't use real numbers between 0 and 1 anymore. What we see here is something we call interference, in which complex probabilities cancel each other out. Interference will be key to quantum computing, as you will see in the next few weeks. But now we've done our first fairly simple example here, where we see interference. And what you could also try at home on your own, you could multiply A with itself. So A times A, this matrix, or we call this I squared. And this actually leads to the identity matrix 4 times 4. And that means these two, we have these two matrices here, and we multiply them with each other. We get the identity matrix, so it just undoes what the matrix does. So you can wonder if this is actually a unitary matrix, or if you have a unitary matrix, you multiply it with its dagger. Try this out at home. But if you take a quick look at the matrices, you should already be able to see whether this matrix is unitary or not. In fact, it is, and that's why we're able to make sure, or that's why we're able, if we multiply A times A, they cancel each other out, and we get the identity matrix. Last week, we also looked at the probabilistic double slit experiment, and today we will look at the quantum double slit experiment. There's a lot of text in here, but it's mainly for your revision, and I don't read all of this out. But you remember the double slit experiment from last week? It was probabilistic, it was simplified, and actually the double slit experiment is a quantum experiment. And just a setting as before, we have 2 slits, and behind we have 5 sensors, 3 each for the first slit and the second slit. And this time it's not bullets, but rather light or photons we move through here with a laser. And we want to see how this actually behaves. And for our double slit experiment now in a probabilistic way, we can again describe it as a graph, which will make it fairly easy to understand from our previous systems that we have established. And I will write this out again on the iPad, and we will see then how to do how the quantum double slit experiment works. So double slit experiment. It's more or less the same setting as before, because we have a start state and then we have these slits. And if before it was a bullet, now if it's a photon that is at slit At the upper slit, it's at position 1. Otherwise, if it's in the lower slit, it's position 2. And this time we use complex probabilities, 1 divided by the square root of 2. And then behind, we have these 5 sensors. We have transition probabilities from these slits to the sensors. So this is position 3, 4, 5, 6, and 7. And we have these loops. Because once we're there, the experiment is over. And we'll look at these transition probabilities. You can find them in the book where this experiment is described in greater detail. I did not come up with these probabilities, but for now we just use them as is, and we'll work with them, and then we'll see an effect that is happening. But as I said, I didn't come up with them. They come from the book. So this is -1 plus I divided by the square root of 6, -1 minus I divided by the square root of 6, 1 minus I divided by the square root of 6, then -1 plus I divided by the square root of 6, then -1 minus I divided by the square root of 6, and 1 minus I divided by the square root of 6. And again, we can represent this as a matrix if we wish. And I will not write out this matrix in detail now. Rather, it's something we will look at the iPad, because it takes quite long to write out these matrices, and usually they don't look very nice when writing them out. So we rather look at it in the slides. We'll quickly look at if this matrix actually makes sense. Well, the first row has to be all 0, which makes sense because there are no incoming edges for 0. There are incoming edges for 1 and 2 from 0. That means we have these two elements here in the second and third rows. And then we have all these loops, which is part of the diagonal. And then we have these other transition probabilities. And for example, we can look at position 4. What does row 4 look like? This one here, it's this one, because it has an incoming one, which is -1 minus I divided by the square root of 6, coming from position 1. And the most interesting one is actually this row here, because it refers to position 5, which has 2 incoming edges, one from 1 and one from 2, which are these probabilities, 1 minus I divided by the square root of 6, as well as -1 plus I divided by the square root of 6. And we have these loops, which are denoted here. Now, we could start with our start state, which is in 0, so 1 and then all zeros, and multiply it with our transition matrix P, and then try to multiply. And then what we have is a state for positions 1 and 2, and we could then have this new state multiply again with our transition matrix P. But writing this down and doing this takes quite some time. You're most welcome to try out this at home, because you have plenty of time for revision, given the course is 5 credits. But what we could also do is we could have one matrix for doing both transitions with one multiplication, and that means we multiply P with itself, which I'm also not doing now because it takes a bit of time. But if we multiply P with itself, and then we turn it into a doubly stochastic matrix. So we turn this matrix with complex values into a doubly stochastic matrix. We've seen also how to do this last week. Or we're not turning it into a doubly stochastic matrix. Rather, we take these complex values and we turn them into real values. We've seen this. The matrix we get is actually supposed to be doubly stochastic, but it's not. We've seen this a bit last week when there were some matrices that were not doubly stochastic, for example, for the double slit experiment. And I said, well, it's a simplification of the double slit experiment from a probabilistic perspective. And if we now look at the quantum one and we turn these complex values with the process we've seen last week into a probabilistic matrix, it's still not doubly stochastic. That means something, and it means that our matrix we have here is actually not fully correct. So this matrix we have here is also simplified. Actually, the double slit experiment is more complex, but we are using this initial matrix to look at an effect that I want to see. But since this doesn't lead to a doubly stochastic matrix, that matrix is probably not correct. And you can check on your own, and you can wonder if this matrix here is unitary or not. Give it a try, and you'll see it's actually not unitary. It's a simplified matrix. But if we have this matrix and we multiply it with itself, we will see something. And what we see is actually this row is most interesting because it now describes two transitions, and we have this 0 in here, which really doesn't look good. And if you multiply these two this matrix P with itself, you will also come to this 0. And it looks very different to the probabilistic one, because I just go back a few slides when we did the probabilistic experiment. We saw that we had this outcome here, where we saw if we multiply b squared with x, we have an increased probability, which is this 1/3. And it has to do with this row. And in fact, with this 1/3 we have here, because it was the probabilistic double slit experiment, and we did two transitions. So from the start state, where it means the photon was in position 0, we have two time clicks, and then we had this 1/3. And now if we do this for our quantum system, we actually, in that spot, don't get any positive or negative value. In fact, we get a 0. What does that mean from the double slit experiment in physics? It means, we just go back to this one. We have these two transition probabilities, but in fact, they will cancel each other out. That means when we do the double slit experiment, we will not have light in this sensor. This sensor will not measure the photon. It's guaranteed to be 0. And this is totally different to the probabilistic one, where we had an increased probability here compared to the other sensors. And now we have not just decreased it, it's actually 0. Because these photons, they cancel each other out. So it's an effect we were unable to see with the probabilistic experiment. And you're most welcome to multiply P with itself as your homework, and you will see also exactly this calculation here, why these two probabilities cancel each other out, and we have a 0 in that spot. And this is one example of interference where probabilities cancel each other out. We'll see interference more in this course, so this was just a motivation for it. There's more text if you want to learn more about the double slit experiment. In fact, the double slit experiment is also explained in greater detail in the book. And take a look at the book if you want to understand the double slit experiment in greater detail. We will not need the double slit experiment further in this course. It was just one example of how we can bring in interference. But actually, this double slit experiment helps us already to introduce a couple of very fundamental principles. We will briefly introduce them now in this chapter, and in the next chapter, we'll look at them in greater detail. One is superposition. So The experiment we have just done could also be done with just a single photon, and that single photon would still cancel itself out in that one spot, because we're working here with complex probabilities. And in fact, what we have created is a superposition, because we don't know for certain where that one photon is. Rather, we know this from a probabilistic perspective, concretely from a quantum mechanical perspective. And so we don't know exactly where the photon is. Rather, it can be in multiple spots. And with a superposition, we say it's in multiple spots at the same time. Superposition Superposition is key to quantum computing. We introduced that term indeed. We already introduced that term in the first lecture and said superposition is important because our system is then in multiple states at the same time, and we can work on that superposition with our quantum operations and thus get a massive speed up. That's the idea of superposition. Then there's also the concept of measurement. And I'm not sure if I talked about measurement before, but I think Horst did a little bit, but I'll just want to introduce this from my perspective. When the quantum experiment runs, we don't know exactly where the particle is. When we want to look at where the particle is, we have to do a measurement. But then we're destroying the superposition, so that we say the superposition will collapse, and we turn this again into a classic system. Measurement is key to a quantum experiment at the end, because at the end you need to measure, and then your quantum system will collapse, and you go back to our traditional world, which is classic and not quantum. This is something we will also need in quantum algorithms at the end, because we will do our quantum, we will start with a start state, we'll create a superposition, we will then do various quantum operations in our quantum computer, but eventually we need classical values, so we need to measure. And the measurement also adds uncertainty, which we will see as well later. There's another term that you will need later in this course. It's entanglement. We will also see this sometime soon. And now you've seen a few, at least initial quantum principles. We have a superposition. That means our photon is in multiple positions simultaneously. And when we want to find out where it is exactly, we need to do a measurement. But then the quantum system will collapse and turn into a classic system. And we got a question here in the chat. Why the matrix is simplified and not unitary. Maybe take a look at the book there. This is explained in detail, but I didn't want to spend too much time on a double slit experiment because it's not much further needed in this course. And you also asked before, I saw one question from before, why this cancels out and it's not A dagger times A. Just look at the matrix, and here A and A dagger is exactly the same, because here we only have real components, so the conjugate doesn't change anything, and when we transpose A, we get A again. So here A transpose is the same as A. We only deal with real components, so the conjugate doesn't matter, and that's why A and A dagger are exactly the same. And that's why A times A leads to the identity matrix. You could also just say A dagger times A, but A dagger is the same as A here. This is something you will also see for various, or for some quantum gates in this course, but not for all of them. If you want to learn more about the double slit experiment, take a look at the book. There's one last principle that we will need for systems. So we've started with deterministic systems, then built probabilistic ones, and then quantum ones. And now we actually want to we want to assemble systems means we want to have composite systems, which are larger systems built from smaller systems. And we will do this in this course now. And just in order to keep this as simple as possible, we're going to use probabilistic systems, but it works exactly the same for quantum systems. I just want to keep the numbers as simple as possible. And for this, I will go back to the iPad and show you these systems, and then we'll see how we can assemble them. And the way we assemble them is exactly the same. And then we will assemble systems. We will have our first system that we call M, and we can describe it as both a matrix as well as a graph. I'll just write down the numbers. You also find this example in the book. And we can have a corresponding graph for M. So we have 0, 1, 2. So 0 has no loop, but has an incoming one from 1 with a probability of 1/6, and from 2, which is 5/6. Then vertex 1 has a loop, which is a half. It has an incoming one from 0, which is 1/3, and an incoming one from 2, which is 1/6. And for 2, it has an incoming one from 0, which is 2/3. And from 1, it has an incoming one, which is 1/3. So this is our first system. And we'll have a second system, and then we'll see how we can actually compose them into a bigger system and what that is useful for, and how to do it very easily. We have a smaller system now that we call N, just a 2 times 2 adjacency matrix, 1/3 and 2/3. Here 2/3 and 1/3. These are doubly stochastic, so they are proper probabilistic systems. And here, for the first system, we call them 0, 1, and 2. And for the second system, we call them A and B, just to keep it that we are able to distinguish them. We don't call them 0 and 1. We could, but we call them A and B, just to make this more obvious. So in A, we have a loop, which is 1/3. In B, we have a loop, which is 2/3. My mistake, 1/3. And we have these transitions, which are each 2/3. And what I want to do now is I want to compose these systems. And composing here means we'll build one big system out of these two systems. So if we have a state that is now called X, it would have 6 entries, because we have our first system with 3 entries, the second system with 2 entries. So 3 times 2 leads to 6 combinations of these positions or entries. And we could say Well, the first entry, and we will just add comments that we actually know what the first row refers to. The first row refers to 0A, the second row to 0B, the third row to 1A, the next row to 1B, and then 2A and 2B. Because there's an order of how we assemble these systems. Means if we assemble M with N or N with M, that makes a difference. We'll see very soon that actually we're assembling M with N, and this assembling here is denoted by the tensor product. Tensor product is something we also introduced last time. Today we'll actually need it, but we'll come to this in a moment. And that means we have assembled M with N, and that's why we have the 0 first, which comes from M, and from N, we have the A here. And if we assemble the N with M, it would be A0, and then A1, and so forth. And if we want a valid state, so remember, it's a probabilistic system here. It's a probabilistic assembled system. The entries need to add up to 1. We could, for example, say, well, the first entry is 1 divided by 18, then 0, 2 divided by 18, 1/3, 0 and a half. If you add up those, you'll see this adds up to 1, so it's a valid probabilistic state. And it's the same rules for quantum systems. So for quantum systems, we said we can also just assemble them if we wish, and their entries, we take the modulus squared of the entries, and they need to add up to 1, and then we have assembled a quantum system. But just for the first system we're assembling, we want to keep it as simple as possible. And in order to describe these transitions in our system, so before we have said, for example, we transition from, say, 0 to 1. But now we need to describe that we have an assembled system or a composite system. So we could have, for example, 0A, and we want to transition to 1B. So we could transition from 0A to 1B, or from 0A to 1A, and so forth. And how can these transitions be described? Well, we can say if we have some state ij, where the I comes from M and the j comes from N, we want to transition to I prime and j prime. We want to calculate what is the transition probability. We need matrix M, and concretely, we need to look into row I prime and then column I. This means how to transition from I to I prime, because the row is the one we want to transition to. Remember this, the column where we transition from. And this is a probability, and we need to multiply this with N j prime j. And now we have all these probabilities here, and we could just try to multiply them all in the right way to build a big transition matrix in order to have a transition matrix for this composite system. Doing this step by step is quite boring, and most likely it will go wrong, but we can do this very easily with the tensor product. Who of you still feels comfortable with the tensor product we introduced last week? Maybe thumbs up if you're okay with the tensor product, or thumbs down if you wish to see a quick revision. So there's at least one thumbs down, so we'll briefly look at that. So we'll just go back to the previous chapter, the maths chapter, where we introduced the tensor product. We said we have two vector spaces, V and W, and we want to build the tensor product of these two vector spaces. was this one here. We said we have our first matrix and a second matrix, and the tensor product just builds a much larger matrix. And the first four entries in this 2 by 2, we put matrix B, and we multiply each entry with the first entry of A. Then the next column, we take A12, and we multiply it with each element in B, and we do the same for the next row. And concretely, if we have this tensor product from 2 times 2 times 2 times 2 matrices, or of two times 2 matrices, this leads to a 4 times 4 matrix. And we briefly introduced this last week, and this week we will see what it's actually useful for. And we can use this to describe the assembling of systems fairly easily. It's much easier and much more generic rather than computing this here step by step. And most likely we would also build a matrix like this, but if we do this manually in a loop, probably it would just go wrong. So rather we use the tensor product for that. And we have our matrix M up here, and we have N up there. So if we multiply this we have a 3 times 3 matrix and a 2 times 2 matrix, that means our tensor product will lead to a 6 times 6 matrix. Concretely, I'm going to say the tensor product of M and N. And just in order to know what each row and column stands for, we're going to use these commons again, as we have used them before. So we had these commons over here, and I'm just going to use them the same. So 0A, 0B, 1A, 1B, 2A, and 2B. These are just commons, that's all. They're not values included in here, but we just know what each row and column stands for, and it's exactly the same order for the columns. 0A, 0B, 1A, 1B, 2A, and 2B. And remember, we take the first element from M and we multiply it with each entry in N. And N is 2 times 2, but this element in M is 0. That means we have 4 zeros up here. Then we have our 1/6, which is next, and we want to multiply this with every element in here. So 1/6 multiplied a third is 1/18th. Just using a different color, 1/18th. Then we have this 1/6 times a third, 1/6 times 2/3, which is 2/18th. Then we have this 1/6 times 2/3 again, which is 2/16. 2 divided by 18. And then again, the 6 times a third, which is 1/18th. And you can keep continuing this, that you just take the next element, like this one, and you multiply it with N, and so forth. It will take you a little bit, but at least it's a structured or easy to follow process, and you will get this transition matrix for the composite system. You can try it at home. The last 4 entries are fairly easy because there's a 0 here. So 0 times this 2 times 2 matrix. That means we have 4 zeros down here. And all these other elements are your homework to try out and see this as an exercise to become more comfortable with the tensor product. If you want to see what the final matrix looks like, I've put it here in the slides. So when I created these slides the first time 4 years ago or so, or 3 years ago, something 3 or 4 years ago, it was fairly difficult for me to create them, and I really had to double check all the entries here in the matrices were fine, and there were still a few typos in the first year, but slowly they got removed, and I think most of the slides look pretty correct. But it took quite some time to typeset these matrices and make sure most of the errors got eliminated. So try this at home, and you will have your transition matrix for the composite system. Now you're wondering, what are these composite systems useful for? So they allow us to assemble systems, build composite systems from larger systems. We can do this for probabilistic ones. We can do this for quantum ones. And in quantum computing, this will be super important that we have actually multiple qubits that we can have worked together through operations, because later, in one of the later chapters, we will introduce qubits, and the qubit is just a very simple quantum system with two entries. So the transition matrix, so it's fairly easy because a qubit is 0 and 1 at the same time. So we have these two entries. But if we want to have more qubits working together, say with an AND operation, you would have with bits, you have 2 bits and you have an AND operation, and you represent each bit as a system, then you need to think about composite systems in order to aggregate multiple bits. And it's exactly the same what we want to do for quantum bits. We want to aggregate them or assemble them and build composite systems. And that's super important just to represent operations that can deal with more than one qubit. Because if you just want to deal with one qubit, it's fairly simple operations like a NOT. But if you want to build more complex operations involving multiple qubits, you need to build composite systems. And that's something we will see in one of the following lectures. There is also a quantum mechanical effect that is called entanglement. And just as a quick teaser, what entanglement is. So we have our composite system, and we build it from the transitions in the two single systems. And now you would think, well, we have all the possible composite states that we can represent with this, but it turns out in such composite systems, there can be states that cannot be broken down into the two individual systems. And these are so-called entangled states. So with compositing systems, and this is something that will come across in quantum mechanics in greater detail, and with these entangled states, you can actually have more complex states that cannot be described by these two individual systems. But we'll see this in the next chapter. It's just a quick teaser. But entanglement will also prove to be very helpful for quantum computing. Now, we have finished the systems here, and what we want to build is quantum gates. We want to have operations working on qubits. But in order to build this, we need to understand quantum theory a little bit more. And we're doing this now in this chapter. And once we have done this, next week, we can actually start doing quantum computing by building quantum gates. You will have a 10-minute break now, and we'll continue then with quantum theory. So, welcome back from the break. In this chapter, we will discuss some of the foundations of quantum theory, some of the things you have seen before, but we'll generalize them a bit. There will be some new things, some new notations, and we'll look at these things, not of all of them in super great detail as you would do in a quantum mechanics course, because we'll need all of this later to work with qubits. And a lot of these things we're doing now in a more generic way will become extremely simple when we deal with qubits. Yet I want to give you a little bit of an intuition to think in terms of these more generic states and the works around there, and it will become more easy to understand a lot of the works around qubits in the next lecture then. The book provides lots of more insights about the double slit experiment. If you wish to read it, take a look in the book. The double slit experiment is not necessary further for this course. But the book also describes one scenario in which would happen. So what we see here is we have the two slits, and we would have most of the illumination, for example, here and there. But just in the middle, where we had before this third target, there's zero illumination, simply because these waves, they cancel each other out, or these photons, what we have seen. And the book proposes some other settings of the double slit experiment, like where one slit is closed, and then the distribution of the illumination would look something like this, and you would not see the interference. If you're curious about this experiment, take a look in the book. There are a few slides to summarize what the book provides you with, but if you want to skip this, I'm also perfectly fine with that. Just if you're interested to learn more. We will now look at a more generic description of quantum states and how we can manipulate them. And we'll see some new notations, and all of this will prove to be very helpful for as of next week when we look at qubits. And for showing you this, I will go back to the iPad, because I think it's more fun to build all of this step by step rather than looking at some slides. So we'll have states and our states in quantum mechanics, they are vectors of complex numbers. So Z0, C1 up to Cn minus 1. So we have n many entries, indexes starting at 0. And a notation we will later use to call such, so it's just a vector, but often these vectors in the literature are denoted with a Greek symbol, psi, and to describe this kind of column vector, we use this bra-ket notation, and this one here, so what I'm highlighting here in red, this notation is called ket. Not the animal, it's just the bra-ket notation that we will see later. And this can be described such a vector as a column vector, or you can describe it as a row vector that you transpose. So this would be C0, C1, again up to Cn minus 1. In the slides and in the book, we sometimes use these row vectors, but actually we want column vectors, and that's why we have these row vectors and put the transpose symbol, just that it's maybe that we have more content fitting on a slide. And we'll come back to this bra-ket notation very soon. But what you will see is that these vectors, they are composed of n basic states. So we have n basic states. So we have a basic state for each element or for each position in here, for position 0, position 1, up to Cn, up to n minus 1. And these basic ones can also be described as a vector because they're basic states. You've seen this kind of work or these kind of things, an introduction to linear algebra and how you map from one set of basic states to others. And we'll also need these basic states here. So the first basic state, x0 ket, can be denoted as a vector. And it's just the first element is 0, and all the other sorry, the first element is 1 and all the other elements are 0. So this is the first basic state. And we have x1 cat, which is 0, 1, and then all the other elements are 0. And we continue with that up to xn minus 1 cat. And here all the elements are 0, except the last one, which is a 1. And remember, we could also just write, for example, the first one if we wanted as a column vector. So this is a 1.
Excuse me,
Or
we're not
0.
seeing your screen.
Oh, well, next time ping me earlier. Then that means most of you were not listening if you didn't ping me before, because if this fails, I don't know, unfortunately. So now it should be working. So what I wrote down was this one here. And I saw one person ping me in the chat, but the chat is on the other device. So I don't see the chat when I write on the iPad. Next time, that means we have, almost 40 people here. That means most of you have not been following the lecture, because if you don't see the iPad, just turn on your mic and tell me within the first 5 seconds, because then otherwise it's fairly pointless to continue. So I'll just quickly revise what I said. We have these vectors of complex numbers that refers to a state. We've seen this concept before. And or maybe you can just tell, because one person said the screen share stopped. Maybe you can tell me, did you see any of this before or none of this? This would be fairly helpful, because I don't know when the screen share stopped then.
Stop us from the end basic state.
Okay, so you saw most of it and it stopped at some point. Okay. So I don't know why the screen share stopped. So we have the basic states, and the first basic state, x0 cat, we can obviously write it as a column vector. And now we can go back to our psi cat and we can try to describe the psi cat as a linear combination of these complex numbers as well as the basic states. So I'll continue with this down here. We have our psi cat. We saw the first element up here was the C0, which is some complex number. And we can say, well, we take this complex number C0 and we multiply it with x0 cat, which is the first basic vector. And down here, I will also write this out in a that we not just have the element x0 cat, but rather the column vector. So 1 and then all the other 0. Then we have our C1 times x1 cat, which is C1 times 0, 1, and all zeros. And we can do this up to element Cn minus 1 times xn minus 1 cat. So something like this. You've learned this in a linear algebra course, how a linear combination works, so I don't need to repeat this. But what we can see is our quantum state, psi cat, can be represented as a linear combination of its complex entries, which are the ones I'm highlighting in red, each multiplied with the corresponding basic state. And our psi cat is a superposition. Superpositions we've seen before, and we've introduced this term. So psi-ket is a superposition of the basic states. And here in the context of quantum mechanics, our psi-ket represents the particle as being simultaneously in all of these locations. The locations are the locations where the basic vectors refer to, with a certain proportion, and the proportion are these complex numbers. But as a superposition, we don't know for certain where the particle is. The particle is simply somewhere in one of these positions with a certain proportion, or sometimes these are also called, these probabilities are sometimes called amplitudes. So these x0, c0, c1, and so forth, we sometimes call them complex amplitudes. And now we want to observe where the particle is. For this, we need a measurement. It's a mechanism we will introduce later in greater detail. And we want to know what the probability is after observing the particles, or when the quantum experiment is over, that we detect the particle at one of these points. So these points are x0, x1, xn minus 1, and so forth. So what I want to know is, I want to calculate the probability of xi. It's very important after observing this. So in the slide, I've also highlighted after in bold, after observing, because it's a quantum experiment. You cannot just observe in the middle. When you do a measurement, then you observe, and then you're done. So we can calculate this by taking the modulus of the corresponding complex number, Ci, and we square the modulus. And we need to divide this by this one here. And you're probably wondering, what does this mean? So I have my psi, which is this one here. It's the vector I've been talking about the whole time, and we're looking at one of its positions, xi, and we need to calculate the, and there's a minor typo, unfortunately, because I wondered it didn't look correct. So we have psi-ket, which is this one here, and we take its length squared. And what this will result in this probability of xi will always be a real number. So P of xi is a real number that is less than or equal to 1 and greater than or equal to 0. Because with this approach, at the end, when we measure, we turn our quantum experiment into classical values. And this is something we can also try out now together with an example. Imagine my psi-ket is the following vector: -3, minus I, minus 2i, I, and 2. And we have here the length of the vector, or the norm of the vector, and we square it, but the squaring will come later. What I want from you is that you calculate, this is a quick exercise, will take you a moment. I want you to calculate the norm, or the length of this vector. And I'll already do the first step for you. The first entry is -3 minus I. We take the modulus of that entry and we square it, then -2i, and we square it, plus I squared plus 2 squared. Remember here, you're still dealing with complex numbers. You can calculate this, and once you have the result, send it to the chat. Please don't look it up in the slides, because the results are all in the slides, but if you just look up what's in the slides, this will not be very helpful for your learning. Now, give you a moment to try this out. So one student says it's the square root of 19. One student says it's the square root of 20. That means we will try it out. So it's a square root, and we have this first complex number, and we want its modulus, and we want to square it. Remember, for the modulus, we have a square root, and we square that, so this just cancels out. What we have here then is simplified 3 squared plus 1, so 9 plus 1 for the first entry, because remember, for the modulus, I need the square root at the end. I cancel this out, so I can just leave it out. So it's 3 squared plus, well, technically speaking, 1 squared plus 2 squared plus 1 squared plus 2 squared. So this is 9 plus 1 plus 4 plus 1 plus 4. And that's the square root of 19. Now, this was the first step, and we'll now apply this. What I want to know from you is, we have this psi, and we've seen how to calculate the probability of the particle being at one of these positions after observing. I want to know this here is x0, x1, x1, x2, x3. So P of x2. That means I need to calculate, we have this I here. So this one from here, we wanted this in the numerator, and in the denominator, we take the square root of 19, which was the norm, and we square it. And you can quickly try to calculate what our result will be. Fairly easy to simplify it, because the numerator is just a 1, and this will be 1 divided by 19. And this is something like 0.52632, and so forth. So you see, these equations here are actually not that difficult. If we look at a concrete example, we can see how to solve it. All of this is in the slides, well formatted. In the slides, you also see one other thing, which is something like this. It's the psi cat, and you have a notation with this wiggly line, and it leads to eventually something like this. This notation here, that you have your state, your quantum state, and you have the basic state. What this or what this notation here shows us, it denotes the state of a quantum system before and after measurement. Because this one here is the measurement, and the measurement turns me the quantum state into a classic state. And the classic states, what we use here, are always these basic states. This is now 4 basic states. When next week, when we look into quantum computing, I told you all of this will get super easy because in quantum computing, we will only have 2 entries, one entry standing for 0, the other entry standing for 1. And what you're doing then is you have your first basic state, which is the classic 0. The other basic state is the classic 1. And when you measure your qubit, it will collapse either into a 0 or a 1. It has a certain proportion, or it has 2 complex amplitudes, but when you measure, you will get one classic value, which is either 0 or 1. In here, we've just looked at this from a more generic perspective and not just with 2 entries, because we're now going to discuss this in a slightly more generic perspective, and then later on move on to simplifying this and looking at qubits. But understanding the qubits will be easier if we've discussed this from a more generic perspective. Then I'll show you a few small things in the slides. I'm just switching to them. So all I've just shown you is well formatted here in the slides. Then we've seen this example here, and there's one nice formatting of this measurement visualization here. And our example from just before. There are a few things around the cats that are actually obvious when you know linear algebra. So you have one state, psi cat and psi prime cat. They are the same length. They both contain complex values. So the Z0 is from psi and the C0 prime is from the psi prime, and you just add these two vectors together. So you add their complex values in each entry. So the first entry with the first entry and so forth. This is here just written in a highly generic perspective, but eventually you get your state, and the first entry is Z0 plus C0 prime. Then the last entry is Cn minus 1 plus Cn minus 1 prime, and so forth. As you can use vectors and you can multiply them with a scalar value, so a scalar value can also be a complex number. You can do the same with our cat notation. You have psi cat to denote a quantum state, and you multiply it with a complex value. That means you multiply each entry with the complex number, as you would do with regular vectors. The literature discusses some other things in detail, like what happens if you have a vector psi and you multiply it with itself. In fact, this is 2 times the vector. So you just multiply 2 with each element. And when you look at the sum of the modulus squared, eventually all of the, and you want to look at these probabilities, say you want to know after measurement, what's the probability the particle is found in position xj? You've seen before how we can calculate this. And the S prime here just refers to the sum of the modulus squared, which is just the length of the vector squared we have seen before. All of this will eventually you just be able to factor out and cancel out. So if you multiply any factor with your quantum state, it changes the numbers proportionally in the quantum state, but it doesn't change the physical system. So like 2 times psi cat still describes the same physical system. And you can replace this 2 with any arbitrary complex number. It will still cancel out. So the length of your vector doesn't matter. So if you multiply it with 2, with 5, whatever, it's still the same physical system. And if you remember from before, when we worked with our systems and we multiplied, say, a state with the corresponding matrix, we always wanted that our states are normalized. And from now on, we can, or until now in this chapter, we didn't assume the states are normalized because we've seen states like this one here. They're obviously not normalized, but we can try to normalize them now. And we can from now on always assume our states have length 1. And in order to do this, I'll show you this on the iPad. We're going to normalize the state. What we can do is we just take our psi ket and divide it by its length, something you can do in linear algebra, classic linear algebra with real numbers as well. You take the vector and divide it by its length. This leads to length 1. So you have normalized vectors. And then if you remember from before, we had this one here. If we have to calculate the probability of observing the particle at a given position, what we don't need anymore is this normalizer if our states are normalized. So this will become fairly easy then, and we can say the probability of finding the particle at position xi is we just take the corresponding complex value and its modulus squared, and this normalizer from before is not needed anymore because we already deal with normalized states. And there will be a quick exercise for us to try this together. We say we have a new state psi ket, and its entries are 2 minus 3i, 1 plus 2i. We want to see how we can normalize this one. So we can first calculate its length, which is 2 minus 3i modulo squared plus 1 plus 2i modulo squared. You can think about what this could be and send the answer to the chat, and we'll compare this momentarily. You can, once you've calculated this, let us know. It's the square root of 17, which is approximately something like 4.2426 and so forth. And we could then normalize our vector by dividing it by its length. And what we could get approximately is something like 0.4174 minus 0.70711i. If we just leave out the square roots now, but look at look at our real numbers, and the next entry would be 0.2357 plus 0.4714i. Something like this, as an approximation. So there's some, oh, should have been probably 18, someone said, so I added them up wrong. I'm sorry. So just double check it. Yeah, should be 18. Sorry, not 17. So I'm not going back, or I'm quickly doing a screen share to fix this. My mistake. So we'll fix this. This number here was correct because this was the one from my slides. So it should be correct. Yes. And all these numbers here were also from my slides. Just the 17 was wrong, but I've worked with the 18 in the remainder of the slides. So, if you want to learn more about how subatomic or about other properties of subatomic particles, you can read lots in the book and in the literature, and there's one subatomic or one property of subatomic particles. It's called a spin. This will play a major role when it comes to implementing quantum systems uh, on a physical computer. For this, the spin is something that can be used, and it's explained in detail in the book what the spin is. And there's the so-called Stern-Gerlach experiment, in which this can be measured. It's something that we don't need in this course because we will mainly look at quantum mechanics purely from a computing perspective as of next week. So we don't need the spin. It's maybe relevant for some of the seminar presentations or maybe some of the slides that Horst Kuhnhardt will talk about again, about the physical implementations. But so far, it doesn't concern us in the next few weeks. So I'm not discussing the spin in detail. If you're curious, there are a few slides summarizing this. You will also find more information in the book. But what you can say is a particle has an up and down spin with certain proportions, and then there are a few examples of how to calculate these probabilities. But it's just the same maths as before, which you would be fairly easy to understand if you want to look at these slides or in the book or not, which is up to you. But from the things I'm talking about in the next few weeks, we'll not need to spin. So this is more like one of the expert chapters if you want to do further readings. And if you're curious about the spin, take a look at it. We started before with this cat notation. And in fact, this is part of something larger that we call the Ra-cat notation. So Ra-cat notation. And we've seen our cats before, our psi cat. And as there's a psi cat, there's also a psi bra. So this is called psi bra. And in fact, this is related to the cat. And it's exactly the same as psi cat dagger. So you apply the adjoint to psi cat and you get psi bra. If you remember from before, we had our psi cat, which was something like this C0, Z1 up to Zn minus 1, which is a column vector. then psi pra will be a row vector because we've seen the dagger operation and we saw, well, one of its two steps is the transpose of a matrix. But if you transpose a column vector, you're turning the column vector into a row vector, vice versa. Because a vector is just a matrix, or a column vector is just a matrix with one column. And if you apply the transpose, you will turn this into a row vector. But the dagger does more, as you remember. We also calculate the conjugate of each entry. So this will be Z0 conjugate, C1 conjugate, up to Cn minus 1 conjugate. Now you'll have a quick task that we can practice this together. Your psi cat is something this, 3 and 1 minus 2i. And what I want from you is the psi bra. Should be fairly easy for you if you remember the adjoint operation. And once you have this, send it to the chat. We'll compare it. And it's 3. The next element is a 1 plus 2i. It's very important. It's a row vector. So the ones of you who wrote this in the chat, well done. Makes a big difference whether you're dealing with a row vector or a column vector. Then we'll see now what this bra cat notation in its entirety is actually useful for. Imagine you want to know the transition probability. So you have states and they are transitioning into other states. What we want to measure, how likely it is that the state of a system before a specific measurement, so the start state, will change to an end state after measurement has been carried out. And in order to calculate these transition amplitudes, we need to calculate the inner product of the state space. And when we deal with the bra-cat notation, this will be fairly easy to calculate. We can have, and I'll do this again on the iPad, even though it takes a little bit longer, but then we'll develop it together step by step. So we have our psi cat, which is C0, C1, up to Zn minus 1. And we have our psi cat, or psi prime cat. So prime here, cat. C0 prime, C1 prime, up to Zn minus 1 prime. They are both normalized states for now. Then it will become easier. And if we calculate the inner product, this will give us the transition amplitude between state psi and psi cat. How can we calculate the inner product? Eventually, the inner product here in this case, it's more or less just a scalar product of the two vectors. But it's not exactly the scalar product because from psi cat, we need the conjugates. So we cannot just do the scalar product here or the dot product. Rather, what we need to calculate is we have psi cat and we multiply this from the right with psi prime bra. This one is sometimes written as in a slightly simpler notation because we have this sign here, and sometimes it's just turned into a comma, but this means exactly the same. So we have here our psi and our psi prime. Sometimes this is written again, because I'm showing you the different notations in a more complex way, but they are all exactly the same. So this is psi or psi prime. And here you have the bra, or you have the cat here and the bra here. And sometimes you just use one of these, as you have seen over here, or you just put a comma. All of that is exactly the same. And what it leads to is, from our measurement notation, we have our psi, and we want to know what's the probability of measuring our psi prime. And that transition probability is just what we have done before, psi prime bra multiplied from the left, or from the left, and then from the right, we take our psi cat. And we can calculate this, or I'll show you now in a generic way how we can calculate this, and there'll be some examples very soon to make this more practical. So we have our psi prime and our psi as from before. And the psi is just a column vector, C0, C1, Cn minus 1. And we had our psi prime up here as a cat, so psi prime cat, but we need it as a bra. That means psi prime bra is the same as the psi prime cat, and we apply the dagger to it. It's what we just introduced before. So that means we're taking, my pen just struggled, wait a second. Somehow my pen isn't working very well right now, sorry. So we apply the dagger to this. That means we get our column vector, which we had just practiced, which is C0 prime conjugate, C1 prime conjugate, up to Zn minus 1 prime conjugate. And we multiply these together. We will finally get a sum of products, and that's C0 prime conjugate times C0 plus C1 prime conjugate times C1 up to the last element, which is Cn minus 1 prime conjugate times Cn minus 1. And this gives us the transition amplitude between state psi and psi cat. We have just denoted here, just a visualization for a measurement. We can try one example together to calculate this. So we have our psi cat, which is square root of 2 divided by 2 as a factor, and it's 1 and I, and our psi cat, or psi prime cat, the square root of 2 divided by 2, 1, sorry, I and minus 1. And what I want you to calculate is this one here. So psi prime bra psi cat. Can take a short moment to calculate this. It's again in the slides, a few slides away. Don't look this up. Try to calculate it. And when you have the solution, share it with us in the chat. We got one answer. Maybe the others can try to come to their answer, to their own answer as well. Two answers. So let's try it out together and see what we get. We have our psi prime cat. We need to turn it into a bra. That means square root of 2 divided by 2. And we have this row vector minus I minus 1. We multiply this with square root of 2 divided by 2 as a factor 1 and I've maybe for those who have done their calculations, they want to look at that again. Just if you have done this preliminary step or not and got the right answer, this will be minus I. So what we have here is we have the minus I times 1 plus we have these factors. So square root of 2 divided by 2. I just moved these constant factors in front. So times minus I. And then we have again, so I'm doing it in a bit of an extended way, just that we're all on the same page. So, and then we have minus 1 times I, so minus I. And what happens here is, so this is 2 divided by 4, it's a half. So a half minus I. And here the same. This is a minus I, sorry. And we have, again, a half minus I. So it's eventually minus I. So I know this isn't that easy when you use all these complex numbers and you have these factors which are purely for normalization. This one here is just the same as 1 divided by square root of 2. If you work with 1 divided by square root of 2, maybe it's easier for you. But in some people prefer to have the square root in the numerator rather in the denominator. That's why I use this example here where we have the square root of 2 in the numerator rather in the denominator. But it looks more complex, but actually it's less complex than it actually, so it looks more complex than it actually is. Always feel free to do these examples at home. Concretely, this example was also in the slides, not with the preliminary steps. It's fairly easy. And what is this useful for? So we need these transition amplitudes when we do the measurement. I've talked about this. The slides contain some more text for revision. Why this is, or a few more details on the basic states. We've seen the basic states earlier today. Concretely, they were here. And what you have noticed is that these basic states are an orthonormal basis. Who of you has heard, say, or remembers this from your linear algebra class, the term of an orthonormal basis? If you remember this, maybe thumbs up. If you don't remember this word, maybe thumbs down. It's something you would typically come across in a linear algebra course. And yes, there are some thumbs up. Our basic states form an orthonormal basis, and an orthonormal basis means so you have two of them as an example, and they are orthogonal. And if all of these basic states in the basis are orthogonal to each other, then you have an orthonormal base. And in fact, this is a maximal list of mutually exclusive end states. And this is something we need in quantum computing. You may see other examples that use different basic states rather than these most simple ones we have used today. But when we go to quantum computing, it will anyway all be fairly simpler because we just have two basic states, 0 and 1, and those are the ones we are working with. Here there are a few more generic notes on orthonormal bases of states, if you care about this, and that you have multiple of them in or multiple of these end states. Later with quantum computing, we just have 2, 0, and 1. And what is denoted here is our quantum system is collapsing into one of these end states. And what we have just calculated are the transition amplitudes for that. If what we have just done works if our states are normalized. If our states are not normalized, then you need to normalize that transition amplitude by the product of the two lengths of these two vectors we have just used. But we said before, from now on, we always assume we are working with normalized states, so we don't need that. This is just another example. Feel free to do it at home. If your states are not normalized, you need to normalize at the end, and you will also get the same transition amplitude that we got before. And there are lots of other ways how you can calculate this, but it all leads you to the same result. But we've assumed we have normalized states, so we don't need this. Now, there are a few terms that you at least should have heard or today, or you should have at least remembered, or you should at least remember this after today's lecture. When you read books on quantum mechanics, we've now looked at states in detail. There are lots of further pages also in the textbook on so-called observables, because there's something that you want to observe in your quantum system. I'm skipping that. There are a few slides if you want to do readings about observables, and there's much more in the book. But because this is a quantum computing course and not a quantum mechanics course, all we care about is that we observe a 0 or 1. And we don't care about all these other possible set of observables. because these can be other physical quantities. But it doesn't matter for this course because it's about quantum computing. There are a few slides if you want to read about the theory of observables. And there are some references to the book where this is explained in greater detail, but we just don't need it. It's just for the curious ones of you who have created this. Then measuring is a term I've mentioned a few times. And I think we already talked about measuring very briefly, maybe in the first lecture. But I'll explain now some more details what measuring means. So we have a quantum system and we are unable to just look at what it looks like because when we do this, we do a measurement and then a quantum system collapses into a classic one. And the measurement itself is also a probabilistic operation. So imagine you have two amplitudes for, say you have a qubit with basic states 0 and 1. And you want to do a measurement and see whether that qubit is in 0 or 1, and you will get out either 0 or 1. Now imagine you have a very large amplitude for the 1 and a small amplitude for the 0. And you measure that quantum experiment once, it will collapse, so the quantum experiment is gone. It will collapse most likely into a 1 because the 1 has the highest amplitude. But if you repeat that experiment and you're just doing the same experiment from scratch and you measure again, it could, for a few instances, you could measure a 0 because there was some amplitude for the 0 and our qubit is in both 0 and 1 at the same time. And when you measure or when you repeat the experiment, you don't necessarily get the same answer as before. A high amplitude would mean most of the times you would measure the 1 because there's a low amplitude for the 0, but not all the time. So the measurement itself is also a probabilistic operation. And there's lots of text in here about this and with some theory, and you can read more in the book. But all you need to remember for this course is if you run your quantum experiment once, you get a certain answer. You run it a second time, you may get the same answer, you may get a different answer. So oftentimes, to get more certainty, the same quantum algorithm is run on the same data many times, maybe a few hundred, maybe a few thousand times, and then you get a distribution of the outputs and you see which output is actually the most likely one. Now you're wondering maybe, does that actually lead to a speed up? Because we've said we do quantum computing that we get speed ups, and now I'm telling you, we need to run the same experiment many, many times. Why does that still lead to a speed up? Because our quantum algorithm may give us a massive speed up, maybe squared up, maybe exponential. And if you just run that same experiment, which doesn't take much time then, maybe 1,000 times, it would still lead you to a massive speed up compared to solving the original problem with a classic algorithm. Yet, if your quantum algorithm just gives you a minor speed up on a very small input and you run that one thousands of times, maybe it doesn't give you a speed up or it's slower than if you just solve this on a traditional computer. But we always assume these quantum algorithms that we're interested in, they give us a massive speed up. We deal with big data. And then if you run the same experiment, say 1,000 times, it's still massively faster than if you run or if you try to solve this problem in a manual way, in a traditional computing way, which then it may actually be unsolvable because the algorithm just is running for forever, say, in order to crack encryption or whatever. And for some problems, like for example, cracking encryption, when you get the output from your quantum algorithm, you could directly validate whether it's actually correct or not, whether it allows you to crack the encryption or not. And if it doesn't work, well, maybe you need to run the quantum experiment again. It's the same with the black box search because it may give you a wrong result, but the result you get, you can check if that's actually the input you were looking for. If so, you're fine. If it gives you something wrong, just run it again. And for other experiments, you just have to run them a few times or maybe a few hundred times to get a reliable distribution of the output. But it's something we'll be seeing in the next few lectures, but I just wanted to tell you what the essence of measuring is that you need to remember. For more complex quantum systems, there's more to consider, more theory. Feel free to read this in the book or here with a few slides if necessary, but we don't need that for the remainder of the course. We will now look a little bit in greater detail into the concept of unitary matrices again, because we've seen them at a few times now, and we've seen how unitary matrices can allow us to undo operations. But in order for this to become more clear, we will extend some of these examples and look at that from a more generic perspective. And that's something I will also describe on the iPad. Imagine you have some, so we're now in dynamics. And you have some quantum state, psi. Oops. So we have psi ket, but we don't just say psi ket, but rather at some time t. This is our state, it's a vector, and we multiply it with u. So U is a unitary matrix, some operation to evolve our quantum state to a different one. And this will lead to psi at time t plus 1 ket, because this is the dynamics. We have our state, and we evolve it to a different state by using our matrix U. And it's a unitary matrix. And soon we'll see why unitary is so important. Now, we could try to write this not just with one U, but with multiple U's. For example, we have our state psi ket, and we multiply it with matrix U1. And I'll get something U1 times psi ket. And now I have this new state, which before we called, for example, psi at time t plus 1 ket. And I multiply this with another matrix, U2, another unitary matrix. And this new state is then U2, U1, psi ket. We could also write this as something like at time t with the notation from before. We could write that this is just the same as, say, psi ket at t plus 1. And for over here, we just go back to before, we could call this as something like psi at t plus 2 ket, and so forth. So we could have a U3, whatever, to continue this. And we've done these operations. So I say U3 ... But we are able to undo this by multiplying from the left. So we always multiply these U's from the left. If we were in this one here, for example, we can go back to our previous state by multiplying this with which matrix? Let you guess this. You can turn on your microphone or send this in the chat. How can I go back from the state at t plus 2 to t plus 1? What do I need to multiply that state with? So someone wrote U1 times U2. Well, I want to go back from t plus 2 to t plus 1. And I need to multiply this state here with one matrix. And we've introduced unitary matrices and some other concept. And we got the right one. Now it's U2 dagger. Because what I'm calculating then is U2 dagger times U2, U1 psi cat. And these two just cancel out because they're unitary matrices. So this is just the identity matrix, and the identity matrix is a neutral element. And here, I could also use U1 dagger to undo this and go back. In the slides and in the book, you find a more generic example with more steps, up to n many steps or n minus 1 steps or something, and then it's undone. But I've just shown you the essence here and probably have shown it in a few more details than it's shown in the book. So if I have my quantum system or my quantum state and I multiply it with U1 and then U2, obviously I'm evolving, I'm getting to new states. But then if I start multiplying from left U2 dagger, then I go back to t plus 1. And if I multiply again with U1 dagger, this will happen again. It's important that you do it exactly in this order. Say if you're in t plus 2 and you would multiply this with U1 dagger, this would not undo it because you're always multiplying from the left. So, and then you would evolve to a new system, but you wouldn't be undoing this. You need to undo it exactly in reverse order as you have done these multiplications. Otherwise, it's not working. This is something we will need for in quantum algorithms, because something that you will see in a few weeks' time in quantum algorithms is that we need to create superpositions, because we start in a quantum algorithm with classic states, then we create superpositions in order to be able to use certain gates that we will still introduce. But sometimes you're creating by accident, say, unnecessarily many superpositions, but sometimes this is something that happens as a consequence of certain gates that you're using, that you're creating too many superpositions, and you need to be able to undo some of these superpositions. Otherwise, your system is too complex, and this will not help you then to efficiently solve your quantum computational problem. So you need to be able to undo certain operations to avoid unnecessarily many superpositions. And that's something we will see in the next chapter when we introduce quantum gates. We will see how to undo them at some point. And all of this works because we're doing reversible computing, and we're doing, in fact, a particular instance of reversible computing. We're doing quantum computing, and we use these unitary matrices. If we didn't want to be able to undo certain things, we wouldn't have to use unitary matrices. But we need to be able to undo certain operations to reduce the number of superpositions throughout the computation. And for that, we need unitary matrices. Because I've promised you last week when we introduced unitary matrices that we would need them at some point. Now you've seen why we actually need them. It will become more obvious when we introduce quantum gates in next week's lecture. So, we've done, so this is just a slightly more generic visualization from the book, but I've shown you this from my notation here in the slides. So how do you feel? Do you feel you got lots of new stuff today? And if you want to see something else, maybe thumbs up or thumbs down if you're okay for today after nearly 2.5 hours, and if you feel you need a break. And maybe some more answers. So I only see thumbs up. That means we can continue. That's good, but we'll still do a quick break for 5 minutes or so, and then we'll continue and we'll pause the recording for now. Now that we've discussed the dynamics, we will look into assembling quantum systems. And you remember in the beginning of today's lecture, after we had finished quantum systems, we looked a little bit into assembling systems, and we did this from a purely probabilistic perspective. It was fairly new concepts, and we needed the tensor product. Now we can try to assemble quantum systems. And I told you before, this isn't more difficult than just assembling probabilistic systems. Imagine we have two independent quantum systems, Q and Q prime. They can be represented accordingly by two vector spaces, V and V prime, and we want to merge them. We want to build a composite system, so we need to take the tensor product of the vector spaces. And we've tried this before for probabilistic systems. And you can do this, obviously, for more than two systems. You can just continue this to build ever larger systems. So you have the first vector space, or the vector space 0 and 1, then vector space 2 up to vector space k. So you can just keep continuing this with more and more vector spaces if you wish. And the tensor product is associative. And we will look at that from a slightly more generic perspective now, because before we've used simply the tensor product to build this. But I think if we look a little bit more into the details, it will. And then we will look at this from a more generic perspective. So say we have one system 1 with n basic states. We have system 2 with m basic states. So now we can look at the assembling of quantum systems a bit more from a more detailed view, because meanwhile we've introduced basic states around quantum around quantum systems, and it just helps us to look at the assembling now and at the interpretation of the tensor product in greater detail. What we can do is we can now do tensor products of the basic states. We can say we have x0 ket. We take the tensor product with y0 ket. So x comes from the first system and y from the second system. This means it's the first particle is at x0 and the second particle is at y0, because we are now composing a system made of two systems. We could also look at the basic state x0, and we aggregate it, or we assemble it with ym minus 1. This means the first particle is at x0 and the second particle is at ym minus 1. And we can continue this with another example. We can say xi ket, and we do the tensor product with
The screen sharing is stopped again.
okay.
Yes.
When did it stop? How
Just
long?
about now.
Okay, thank you. Because I don't notice this. I'm on the other device. I'm sorry about all these Zoom issues today. And also for the ones watching the recording, we had to cancel or stop the recording a few times in between when there were other strange issues with the screen sharing. I'm sorry about this, but thanks for pinging me. So it's xi and yj. Just trying to write a nicer j. And we do of these basic states the tensor product. That means the first particle is at xi and the second particle at yj, and so forth. So this is the interpretation of the tensor product. And now we assume we have two systems. System 1, we have n equals 2, and we have our system 2, we have m equals 2. Then we can think about what are the basic states of the composite system. And in fact, to build the basic states of the composite system, we need a tensor product of these basic states of the individual systems. So I'll write down a set now, and that set is actually the set of basic states for the composite system. We have our x0, which is one of the basic states of the first system, and we take the tensor product with y0. So this is now one basic state of our composite system. The next one is x0 cat, and we take the tensor product with y1 cat. It's the next basic state. Then we have the x1 cat, take the tensor product with y0 cat. And the last basic state is the tensor product of x1 cat and y1 cat. So this set denotes the four basic states, or it's the standard basis of the composite system. And when we now look at a state in at some state psi cat, which is a state from the composite system, it's eventually a linear combination, or in this case, a superposition of these basic states. So we could say it's C0, 0, which is the amplitude, and then the first basic state is x0 cat tensor product with y0 cat, and then dot, 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 up to C11 times x1 cat, and the tensor product of this and y1 cat. Oops, no, obviously no set, sorry. So, and this dot, dot, dot refers to the two other components. So this is what our state psi cat in this composite system would look like, and it's a superposition of those four of these four basic states, which are the tensor products of the basic states from the individual systems. And in the slides, you can find even a more generic one. I'll probably not write that one down, rather quickly show it to you. The slides, we see even a more generic one. We see this psi cat. It's C00, 0, the amplitude, times this basic state in the composite system, which is x0 and y0, and the tensor product of these two, plus dot, 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 up to Cn minus 1, m minus 1. It's the complex amplitude. And you have the corresponding basic state. It's x1 minus 1 cat, and the tensor product of this with ym minus 1 cat. And then you have obviously this index I for all the other indexes I and j for all the other ones in here. So Cij times the tensor product of xi cat and yj cat. And we are working with an n times n dimensional complex space, C n times m, and we are dealing with these complex numbers. So this is our generic description of the linear combination of a state in this composite system, or in this case, it's also a superposition because we're dealing with quantum. And we got a question. If I can swap to Teams. No, I'm never going to swap to Teams because Teams creates far more problems. I just don't know what's wrong with Zoom today. It's probably the update that came in a few days ago. I'll try to fix that until next time, but there's no way I'm ever going to use Teams for teaching and recording lectures. Zoom overall works far better and offers better features, but there are some issues today. I know that. And the question is, what is C00? It's not well, it's not necessarily the product of the two amplitudes. It's just one amplitude in that state. Because if you have a state and the other state, we've seen before how we can assemble these systems and these transition probabilities. But it doesn't mean we're just multiplying the two complex numbers with each other. Rather, this is just a generic description. And well, we could have two states and we could multiply these complex numbers, but we would still need to normalize all of this that it works. But we don't care too much about the concrete complex numbers anyway. Before, we cared more about the transition probabilities, and we've seen how to build them with the tensor product. You could multiply these two complex numbers, yes, but you would still need to normalize all of them that they add up. But it's just a system that is evolving, and C00 means it's the complex number referring to that basic state. Cij is the complex number matching or for this basic state, and so forth. So hope this answered the questions. And as we've done before, and for this, I'll switch back to the iPad. We've seen before how to calculate this probability here for a single system. And that kind of notation can be used as well for a composite system, that we would say we take a probability and we need to divide it by its normalizer. So, but a normalizer here in the two-particle system. And I would show you how we can do this for one concrete example that I've prepared. And then we'll see how we can calculate these probabilities in a two-particle system. And all of this can be applied as, again, to more than two particles if you wish. The quantum amplitude Cij, it's concretely the modulus squared, gives us the probability of finding the two particles at positions xi and yj. So we could just take this one if the system was normalized. But one could think about systems that are not normalized, and then you still need to normalize, and that's exactly what we are doing now. So we have our psi cat, and psi cat is now from a 2 times 2 system. It's I times x0 cat, the tensor product with j0. And then we have 1 minus I. Well, I'll just write this just move this somewhere here that we can have always this at the same distance. So x0 and y1. I'm just writing down this first x1 and the tensor product with y0, and then x1 and the tensor product with y1. And we have these, the corresponding complex amplitudes. So one was I, then we can say one is 1 minus I, then 2, and -1 minus I. And what I want to know now is the probability after measuring the two systems, finding the first particle in x1 and the second particle in y1. If the system was normalized, I could just take this probability or this complex amplitude, take its modulus squared, and I'm done. But the system is obviously not normalized. So I need to normalize this, and I could normalize either the whole system, or I could just calculate, as we've done before with a single system that was not normalized, we could say -1 minus I modulus squared. This is the probability I want, but I need to normalize it by saying I use the sum of all of their modulus squared. So it's the modulus squared of I, it's the modulus squared of 1 minus I, it's the modulus squared of 2, and the modulus squared of -1 minus I. You can try to solve this briefly and then send us the result here in the chat, what you think the answer could be. And one student suggests it's 2 divided by 9, which is around 0.22, and so forth. So that's correct. Thank you very much. And if you normalize the system, because you have the normalizer here, you could just normalize all of these probabilities and then take directly the normalized complex amplitudes, that one's modulo squared, and you're done. You can also find this example here in the slides, and we're done with today's content. So we're finishing now with assembling quantum systems. Next week, we will, and you should take some time to revise all of this. Next week, we will continue a little bit with assembling quantum systems, and we will see an effect called entanglement. I had briefly mentioned that effect today at the end of the last chapter, but we will look more into the issue or into the phenomenon of quantum entanglement in quantum mechanics. We'll see it's something that confuses a lot of people, but it can be a very helpful feature for computing. And we'll finish this fairly easy next week. And then next week, we can finally dive into quantum computing because we have laid all the foundations around systems and quantum mechanics and maths. And we will finally be able to look into qubits, and we'll be able to describe them with all the tools we have now. Plus, we can look into quantum gates and reversible gates in general. We can look at the fundamental gates in quantum computing, as you have the fundamental gates in classical computing, not and or. And we will first next week describe our classical gates with our tools we have now. And then once we have done this, we will build quantum gates from the same methodology. That will be lots of maths next week again, but it's just the maths we have already done. And we will constrain ourselves just to the standard or the basic states 0 and 1, not more, as we have seen here. And but we also need assembling quantum systems when it comes to quantum gates and building quantum circuits. So make sure you have enough time to revise all what we have done today, so that you're prepared for next week. And as you see, we are progressing quickly with the course. In a couple of weeks, we will also be able to look into theoretical computer science, selected algorithms, into concrete architectures. That's something that Horst will teach. And there will also be a programming assignment for you. And so we are soon halfway, or in terms of the slides, we are about halfway through. Content-wise, there's still a lot to come, but as you know, the second half of the term is anyway reserved for you to prepare your seminar presentation. And I'll say more about the seminar presentation in 2 or 3 weeks once we have progressed with most of the content. If there are no questions from your side, we are done for today. I wish you a good weekend. See you next week. Bye-bye.